Okay, so let's start the webinar. Good afternoon, everybody from Europe, and good morning, I guess, to everybody from overseas, from America. And hello to the rest of the world. And welcome to the webinar, How to Improve Your Free Space Optics Communication Using Adaptive Optics. My name is Armin SCHIMPF. I am the team leader here at Alpao of the AO Systems Department. Okay, a few words up front. So we made this presentation for a target audience that has some background in a technical domain, ideally in optics or astronomy, and little background in adaptive optics or free space optics. The objective of this presentation is to give you some insights on how FSO and AO works. If you have some background in FSO, you might be interested on the constraints the integration of an AO system imposes on your application. You might be interested in what is the rough order of magnitude cost of an AO system. And we also give you some hints on how you could get started with integrating AO in your system. So the outline of the presentation, the talk will be roughly 30 minutes, and please really feel free to ask questions whenever you want. So please use the Q&A tool that is integrated in Zoom to ask questions at any time. And every about 10 minutes, I will make a short pause to see if there are questions in the pipeline, and I will try to answer them. Okay, so the outline will be, I start with an introduction to FSO and AO. Then I'll focus on satellite FSO, first the downlink correction scenario. Then we go to the uplink connection scenario. I will give a couple of engineering aspects with regard to integration of the AO system in your telescope. We compare this application to astronomy, and from there we derive requirements of this application on the AO system. So let's get started with the introduction to FSO. Free space optics basically means transmission of light through an unguided medium. Might be for communication purposes or for other purposes. Whenever it's transmitted through an unguided medium, such as air, water, free space, basically when there is no fiber involved, no bulk optics, we call it FSO. So the SATCOM market, which is part of the FSO market, is a really busy market. In 2018, it was worth $23 billion US, and it's projected to grow up to $41 billion in the next 5 years, with an annual growth rate of about 7% per year. The major driver in the FSO market is satellite communication. So let's look at the technical aspects. We see here on the left side a schematic of a communication scenario between a satellite and different ground stations. We have here separate ground stations dedicated to uplink, which means communication or data flow from the optical ground station up to the satellite. And we have the downlink scenario, which means light flow, data flow from the satellite down to the ground station. So in this scenario, the light needs to traverse the atmosphere. And as you know, atmosphere is composed of different layers of air with different densities, with different temperatures. It's an inhomogeneous medium and with different wind speeds. And all of this leads to a constantly changing medium, which degrades the optical link, and therefore it causes fading at your optical receiver. So this can be improved through adaptive optics system. And we see on the next slide how this is working. So we have here a very classical schematic for a AO system in closed loop fashion. The light up here comes through the atmosphere with a wavefront that is distorted by propagation through turbulent layers. This light incident is hitting the surface of a deformable mirror, which we have here. From there, it bounces off, and we will take part of this light to measure the wavefront with the wavefront sensor right here. This information is given to a controller of the feedback control system, which computes as fast as possible the appropriate shape of the DM that allows to flatten the wavefront. And if this is properly working, the wavefront here can be transformed into a wavefront which is much flatter, not perfectly flat. I mean, there's always some residual error. And we want to do this because a flatter wavefront translates to a higher concentration of energy into a smaller spot. So this is really the same goal if you do imaging or if you do FSO. So that's the takeaway message from the slide. Okay, so now let's go into some more details and look at how AO works with satellite FSO. On the left side, we have a schematic that really resembles the one we just saw of the telescope right here. It's really almost a classical AO setup with the difference that the light in this scenario is not used to do imaging. It's used to be focused on a receiver for telecom. And this can be a photodiode, it can be a fiber. So in the scenario of a fiber, the goal is to optimize the light injection into typically a single mode fiber. So you have to achieve mode matching between the fiber mode and the incoming wave. And again, this is the same goal as in classical AO, to concentrate energy on the smallest possible spot. So, okay, for the downlink scenario, now let's look at the uplink scenario, which is a bit more involved. Okay, so in the uplink scenario, we have, for example, a setting like here. Satellite is flying over the optical ground station, and we are looking at a scenario with bidirectional communications. So we have a downlink beam coming down from the satellite, and we have an uplink beam that wants to go back to the satellite. So let's look here on the right side, how the AO system typically looks like in this kind of scenario. The downlink beam is sketched in blue, and the uplink beam that goes out of the telescope is in red. So what happens here is that we need the downlink beam for the AO because we use it as a beacon, because it travels through the atmosphere and it contains information of the current state of the atmosphere, which we can use for AO to deform the DM such that we pre-distort the outgoing beam. And because of the reciprocity principle in optics, this pre-distortion will lead to a flatter and more concentrated wavefront on the satellite side. So let's go through the system. We have the downlink beam coming in here, received by the telescope. It's hitting the DM. From there, it goes through a beam splitter, and this is really classical, sensing by the wavefront sensor, and the RTC commands the DM to put it in the right shape. And then in parallel, really at the same time, we use a very strong laser, the uplink source, which goes through the same optical system, hits the DM, and therefore leaves the telescope with the pre-distorted shape. So we will gain, of course, something by this technique, but it also creates new challenges, and we will discuss these on the next slide. So we're going to talk about the pointing that is needed to really hit the satellite. Let's look at the schematic on the left side. So we have the downlink beam, the receiving beam coming from the satellite, which we use as a beacon. And we have the outgoing beam. And there is one differential element between these two beams. It's the pointing. Why do we need this? Because when we want to point at something that is moving, we need to point a little bit ahead. It's like throwing a ball to a running person. If you really throw it to its current position, you're not going to hit the person. And with photons that also have a finite speed of propagation, it's really the same phenomenon. So we need to point ahead in order to have the photons ready at the right location at the right time. And this point ahead angle depends on the orbit. For geo orbits, it's typically about 20 microradians, which is 4 arcsecond. And for the further you go down, the more you have to point ahead, because your satellite is going to get faster. And when you arrive at the LEO orbit, the point ahead angle can be as large as 50 microradians, which is about 10 arcseconds. So, of course, the atmosphere is different between the receiving and the transmitting path. So when we use the information from the receiving path to precompensate the transmitting path, we make some error, and this error must be considered. It must be included into the overall error budget to see if it's actually worth to use an AO system and for this kind of scenario and application. So let's see how we can quantify this error. You'll see we have to compare this point ahead angle to some kind of atmosphere characteristics. And here we are going to learn to what kind of characteristic we have to compare it. So the atmosphere can be characterized by what we call the atmosphere coherence length. It's also called the Fried parameter, most often just denoted as R0. And this can really be seen as the size of a patch in which the turbulence, the atmosphere, can be considered as constant. Next, we have to further look at the atmosphere, and very often we have a single, sometimes we have multiple, but let's, for the sake of pedagogics, we use only a single turbulent layer in this example, which is going to be at a height h above the telescope, and these two characteristics, so R0 and h, lead to a characteristic angle, which we call the angle of Anisoplanatism. I got that pronunciation right, I think, I hope. And so now let's look at it at an example for an okay observation site. Not great, okay. So we might have a turbulence layer at a typical height of about 10 kilometers and R naught of 10 centimeters at the observing wavelength. And this leads to a anisoplanatism angle of about 3 microradian. So this is the angle when you look up at the sky that can be considered as an angle in which the atmosphere is constant. So we have to compare this angle to the point ahead angle. And if you remember, for the geo scenario, the point ahead angle was 20 microradians. So it becomes obvious that there is error introduced into the system due to this isoplanatism effect. And again, it needs to be considered. It's really the major challenge in the uplink scenario. Okay, so I already talked for 60 minutes. I promised to look at the Q&A tool. Okay, so far no questions. Really, I'd be happy to answer your questions. And maybe later on you have some questions. Okay, so I just continue. Okay, let's look at some engineering aspects, really various different aspects of engineering. First of all, for the uplink correction scenario, there are multiple kinds of configurations that you can consider for your telescope. There is the so-called monostatic design, where you have a single telescope and a single adaptive optics bench for the transmission and the receiving path. Problem with this configuration is that the transmitting and the receiving light, they have orders of magnitude of difference in terms of power between them. You might receive a couple of microwatts, and what you send up there are a couple of 100 watts. So you really have to do very careful engineering of your optics in the optical bench to avoid that laser absorption in your system, in your telescope, will create local heating, local seeing due to local turbulence. And also the slightest reflection of transmitting light into your instrument will create a pollution of your receiving path, which is going to affect the AO system as well as the communication receiver. Another possibility, which is of course more expensive, is a bistatic design, where you have a dedicated telescope for transmitting and for receiver and for the receiving side. So basically the uplink telescope works the same. You just keep the same telescope and you add a second telescope for the downlink only, which will allow you to increase the performances on your downlink scenario, on your downlink system. Okay, I have a question. Let's see. Okay, so the question is, how can I determine which DM I need according to my seeing? Okay, very good question. So we have a rule of thumb that is for good correction, you need as many actuators across the pupil, so across the diameter of your telescope, as the relation between the telescope diameter and the Fried parameter. So a simple example, if you have a telescope diameter of 1 meter and a Fried parameter of 5 centimeters, which is strong turbulence, then you might want to use something in the ballpark of 20 actuators across the pupil. You will still have a gain if you use only 10, but this is what we call partial compensation. If you want to have better compensation, then you might want to use more actuators. But these kind of considerations, they have really to be analyzed as a whole by analyzing all the errors that contribute in your system. And the goal typically is to have a what we call equalized error budget. So it doesn't make sense, for example, to put a lot of actuators if you have a controller that's not so fast, not fast enough. Huh? So you have to analyze each contributor in your error budget and see to have them have almost the value. Then you have an optimized system. Okay, thanks for your question. So I will continue. Next, we have next engineering aspect is the instrument location, which is a very important question. So there are many different foyers at a telescope. I choose to present 3 of them: the Cassegrain foyer on the left side, the Nesmith foyer here in the middle, and the Coudet foyer on the right side. So let's start with the left side. If you attaching the AO system to the Cassegrain port will lead to an instrument that follows inevitably all the movements of your telescope, so azimuthal as well as altitude movements. So it's not really great for large footprints systems. So for small AO systems, this is really the way to go. Alignment is relatively simple in this case because you have only 2 reflecting surfaces. Cable management is a bit more involved because your instrument is moving. Then we have the solution of the Nesmith port. This is for intermediate size instruments because here they will follow only the azimuthal movement of your telescope, not the elevation movement. So this is good if you have applications where you have to look at faster targets, for example, a LEO orbit. Alignment becomes a little bit more involved. Differences are small because you have 1 more reflecting surfaces. Cable management as well. It's a bit more complicated, but it's doable. And last but not least, we have the Coudet scenario, where which requires really a more complicated telescope setup. You see, you have many more reflecting surfaces. And in terms of your building, you need a Coudet room below the telescope. So the advantage is in that room, you can fit in pretty much whatever size of instrument you want because it's not moving. For example, if you have an AO system for the uplink, where you need to have your laser on the table, this might be the way to go. So that's also, the instrument is not moving, so it's working well for really fast targets. Alignment is much more involved. So that's definitely something to take into account. Environmental control of your system is easier because it's in a separate room, and also cable management becomes much easier. Okay, so we are 23 minutes into the presentation. I have 2 questions, which I am happy to answer. Okay, the first one I already answered. The second one is from Mr. Bacci. I hope I pronounced that right. What determines the size of the mirror? So beam size, or we have to add collimator to the AO system so we can adjust beam size according to the DM size. Yes, pretty good question. So you definitely need to, if you have a telescope that has an imaging plane somewhere, you definitely need to add at least 1 lens, typically, to allow the imaging of your telescope entry pupil, of the mechanical aperture of the stop of the telescope. This plane needs to be imaged on the surface of the DM. And you have to add the optics that allow you to have the right magnification between the entry pupil of your telescope and the DM. So if you design your system from scratch, I'd say pick your DM that really fits best your system and just adapt the lens. If you have already a system, then it might be easier for you to choose a DM that has the right diameter. Okay, I hope I answered your question. Let's go to the next slide. Next aspects for engineering is the input information you as a client could provide to us as a AO provider, and which allows us to tailor-made systems for you. So for that, first of all, it's important to understand that AO serves not only to correct the turbulence of your atmosphere, it also serves to correct the imperfections of your instrument and of your telescope, which can be under certain circumstances, which can have an impact which might be as bad for your receiving performance. So ideally, your site should be well known, well characterized in terms of turbulence strength and wind profile. If you don't know how to do this, you can ask us. There are private companies on the market that provide this kind of services. Also, your telescope should be well known and characterized. I'll give a couple of examples. Your telescope, due to wind shake, it's going to vibrate, and as every mechanic is going to have a certain vibration spectrum, and these vibrations, they will create tip tilt as seen by the wavefront sensor. So this tip tilt jitter spectrum and amplitude, it would be interesting to know this spectrum, because we have to include this in the tilt budget for the deformable mirror. Also, pointing accuracy is a characteristic of your telescope that would be important to know for us, because if the pointing accuracy is low, we might need to add a dedicated tip tilt mirror into the system that can compensate for these errors. And last but not least, AO will of course serve to correct static errors of the telescope. So if they are large, then this has to be foreseen as well. Another important aspect is software interfaces between the AO module and the operating control system. So we have three blocks here: the telescope block, which is supposed to represent the operating control system, AO block, and the communication block, which has the receiver. So just a couple of examples of data flow between these different entities. For example, your telescope might be able to accept offsets in terms of pointing and in terms of defocus. When you're tracking and your target goes farther away or approaches the telescope, defocus might add up on the DM. And to avoid pushing the DM into saturation, it can be important to regularly inquire the DM status in terms of tilt and defocus shape in order to offload these modes from the DM to the telescope. Another example is the computation of the point ahead angle in the uplink scenario. As you might remember, the point ahead angle is also steered by a tip tilt mirror that is on the optical bench, on the AO bench. And it depends, of course, on the current position of the telescope, on the target. So that's an information that goes from the operating control system to the AO. And last but not least, AO is, of course, there to correct wavefront aberration, but the ultimate goal of AO is not to have a nice flat wavefront, it's to have an optimized injection into your receiver. And for that, we need feedback from the receiver side to the AO part. So that's also something that needs to be foreseen. Okay, I have a couple of slides left. There's one question. I'm going to take it. What is typically the stroke needed to compensate vibration? Honestly, I'm not sure if there is a typical. It really depends on the telescope. I've seen vibrations up to fractions of arc seconds. And in terms of budget, from what I remember in the systems I have designed, it could be as much as 50% of the overall tilt budget of the DM. So this is especially important because for these applications, you need fast DMs. And most DMs, the faster they become, the less stroke they have. So this is something that is interesting to analyze beforehand to avoid surprises. Thanks for that question. So I continue. A couple of slides left. So now let's see what kind of specific requirements FSO imposes onto the AO system. For that, I start with a small comparing summary between astronomy and FSO. I mean, it looks pretty much alike, these two applications, but there's still some differences. So in terms of object, in astronomy, objects are moving slowly. Sidereal tracking is 15 arc seconds per second. In FSO, it depends on the orbit. GEO is 0, but LEO can be as fast as 4,000 arc seconds per second, which leads to gigantic apparent wind speeds that need to be handled by the speed of your AO system. For optical engineering, there are a couple of differences. In astronomy, you're looking typically at objects that are at infinity, whereas FSO can be as close as a couple of 100 kilometers. In terms of optical design, here it becomes a bit simpler in FSO. Objects are typically what can be faint in astronomy over the spectrum of interest, can be visible or infrared. Whereas in FSO, you have more photons available normally. So error due to measurement error of the wavefront sensor is less of a concern. And optical design is a bit less involved because very often it has to be optimized for a single or for two wavelengths only. A huge difference is operation time. Astronomy, typically we look at we do observation during nighttime, whereas FSO is supposed to work 24/7. So during daylight, you have also stronger turbulence. The sites in astronomy, they have dedicated sites that are chosen typically for their quality of seeing. They have weaker turbulence, and little scintillation. They're chosen to have clear skies, whereas for FSO, deployment of optical ground station that cannot always be on the top of a mountain. It might be close to a city. It might have spurious lights. You have stronger turbulence to cope with, and potentially scintillation. So this is something your wavefront sensor has to cope with. Yeah. And all these particularities of the application, they translate to special requirements on the AO components. Let's start with the DM. For example, if you, for a uplink precompensation scenario, the DM will need to reflect the light of the transmitting laser, which is on the order of a couple of hundred, maybe even a kilowatt of power, continuous power. So it needs to have a appropriate coating, and it needs to have a very high laser-induced damage threshold. Daylight operation leads to strong turbulence, as I said, which translates to a need of a large amount of actuators, of course, in proportion to your telescope size. The RTC needs to be fast, since it needs to potentially handle large apparent wind speeds. The wavefront sensor needs to have a high quantum efficiency in near-infrared wavelength, especially in 1.5 micrometers. Strong turbulence will also lead here to a need for a large number of sub-apertures, and your image processing routine need to be able to handle scintillation. And of course, as always in atmospheric turbulence applications, we have to go fast, so the wavefront sensor needs to be able to run at a couple of kilohertz typically. Last but not least, for optical ground stations that need to be portable, AO system needs to have a small footprint and mass. So here we have an example of an entry-level AO system for this application, DM with 97 actuators, which is able to compensate for about 12 radial orders in terms of Zernike polynomials. A wavefront sensor which provides about 70% of quantum efficiency at 1.5 micrometers, which is able to run at a really high frame rate of 5 kilohertz, and the whole combined with a RTC that is able to cope with this cadence, with this frame rate, and which can provide correction bandwidth up to 215 hertz. So ROM cost for this system is about 100 kilo euros. Okay, so I'm almost done with the presentation. The conclusion is presented here. So I started with an introduction to FSO and AO. I then followed with a explication of downlink and uplink correction in satellite FSO. I went into a bit more details in the uplink scenario, explaining head pointing and anisoplanatism. And then I talked about a couple of engineering aspects, software, mechanical interfaces, stuff like that. And finally, I derived particular requirements on the AO components. Okay, so I hope you liked the presentation. It's already my second one today. This morning at 9 o'clock, I made another one for another part of this work. I'd be really happy to discuss with you, me, my team, our sales engineers, to discuss details about your application, about your potential needs. So really getting started, the easiest thing for you is just drop us an email, schedule a Zoom meeting, a Teams meeting, whatever you wish. And yeah, we can start with a chat. And I see there's one more question. Please feel free to ask questions. So there's a question from Mr. Krömer. What is the typical energy in the light beam involved in FSO? Typical energy for the uplink beam is a couple of 100 watts. It can be as much as a kilowatt, something like that. Okay, we have some time left. I went a bit overboard with my timing. So if you have any more questions, I'd be happy to answer them. Otherwise, you can drop us an email. I think my colleague here who handles the administrative part will be happy to forward them to us. By the way, it's Charlotte who organized the meeting. So thank you very much for your work as well. And yeah, so I see there are no more questions. Then I propose to finish the webinar. Thank you very much for joining us and hope to talk to you soon. Bye-bye.